we find displacement variables of the joint. So this is all your understanding about the motion behind robotics in industrial robots. So displacement variables, if I know, I am able to compute the position where the end effector is being located. We call it as forward kinematics. Knowing the end effector's position, if I am able to recompute the displacement of variables in joints, then it is called as inverse kinematics. So this is all about the study of motion with respect to industrial robots. Now, the next thing what we need to know, how we will compute this displacement variable, how we know the end effector position, all will be done through a matrix called HTM. So this HTM is called as homogeneous transformation matrix. It is a 4x4 matrix. So the whole matrix is 4 cross 4. In that, we have first 3 cross 3, then a 3 cross 1, then a 1 cross 1, and 1 cross 3. Okay. So 3 cross 3 gives me the rotation, or we say it as rotational matrix. This we call it as translational or linear movement. This is for vision, perspective of vision, and this is for scaling. So a homogeneous transformation matrix contains all these phenomena with respect to the end effectors, rotation, translation, followed by vision and scaling factor. Preferably, we will have this matrix understood with respect to rotation and translation. That is, if I have a joint movement from A, if I have a joint movement from B, it may be rather rotational or translational. If I have a joint movement from C, it can also be rotational or translational. If I combine together, what will happen to my end effector's position? That is composed with the help of this HTM, homogeneous transformation matrix. For computing this, we need to know about DH rule, Dinowitz and Hattenberg's principle, or Dinowitz and Hattenberg's theory. So Dinowitz and Hattenberg together has created a principle behind in computation of the displacement variables into a table, and after which it can be projected to a homogeneous transformation matrix. So this is all about the basics behind understanding the motion of industrial robots. So we need to learn about more mathematics here. So the mathematics starts from representing an equation or in representation with respect to a matrix. All is required for learning. So this is one part where we will understand about knowing the displacement variables where the end effector is being positioned in a 3D space. The next aspect is, if I am moving the robot from one point to another, will it move randomly, or will it have a path constraint, or will it have a trajectory? So we need both understanding about what is path as well as trajectory. So in robo, we talk about path planning with respect to acceleration and velocity. So the next part is, after forward and inverse kinematics, we will study about path planning, trajectory. So what is path? Path is a series of points which joins from starting to the destination. Okay, so we find intermediate points in between. So this categorizes how the path is being put forward. So I can choose a different path for different movements, but is that movement feasible? So a robot application area, a workspace, the confinement, all depends with respect to the customer's requirement. So the customer's requirement may change, an obstacle may be present in between. So if that is the case, I need to choose a different path for the robot. So all comes under path planning. What is trajectory? Again, a path being governed knowing the future location, predicting the future location with respect to acceleration and velocity along with intermediary points, we call it as trajectory. So for these we require polynomial or polynomial representations. What is polynomial? You know about polynomials. A degree polynomial of 1 will have an equation of y is equal to mx plus c, where the power of the variable x is 1. The degree is 1. So if I need to go for a rather higher degree of polynomial, I will go for ax square plus bx plus c, which stands to be the 2-degree polynomial. If I go for a 3rd-degree polynomial, then again ax cube plus bx square plus cx plus d is equal to 0 is a representation for understanding the degree of polynomial. Okay, so this is for understanding. But for creating a path, which degree polynomial is required? So I will require a cubic polynomial as a minimum if I am creating a path for the robot to function. So it will require a 3-degree polynomial or a cubic polynomial. Why a 3rd-degree polynomial is required? If you ask me, say for example, I have an equation called some ax plus b is equal to 0, which is a degree of 1. If I differentiate this with respect to x, why I differentiate, I will tell you. So dx by, or we can say it as in terms of at plus b. So this is an equation x continues to at plus b is equal to 0. If I differentiate the x equation with respect to time, what I get is a. If I double differentiate that, the value will be 0. Supposingly, if I take a 2nd-degree polynomial like this, ax square plus b, at square plus bt square plus c is equal to 0. This is representing a x equation. If I differentiate that dx by dt, I get 2at plus b. If I double differentiate that, I get 2a. So this represents the first derivative, differentiation of the equation with respect to time. Upon the first derivative, I get a constant in 1-degree polynomial. In 2nd-degree polynomial, I get a constant here at double differentiation. So this should not happen. Why? So the first differentiation with respect to x, if x is notified as displacement, if it is a straight line, I may have y is equal to mx plus c. If that is a straight line I am representing, if I differentiate that, which gives velocity terms, displacement if differentiated gives velocity terms. If I double differentiate that, it gives acceleration terms. So look at the first degree. So if I am having a straight line, if I differentiate that displacement what is being given, I get the velocity as constant, which is not permissible. And if I double differentiate that, the acceleration becomes 0, which is also not permissible. So if I go for 2-degree polynomial, I will have velocity to pertain with respect to time, whereas acceleration becomes constant, which is not permissible. And that is why we require a cubic polynomial for representing a path. So a path is always being confined with respect to a cubic polynomial, which is a degree of power 3. So if I have power of degree 3, I will have the differentials for the first order differentiation as well as the second order differentiation, which is nothing but your velocity and acceleration to pertain with respect to time, rather it becomes a constant or a 0 value. So this is all about path planning. So if I am creating a path for the robot, this path of the robot should have a starting point and destination, which is governed by the equation, and the governing equation should be a minimum of cubic polynomial. So in path planning, we also have a smooth transition planning, We also have a spline trajectory planning. All these are um, subparts that just need to be learned when we go for path planning techniques. So again, I'm giving you a clarification that if I am planning a path is nothing but a starting and destination point governed by intermediary locations, whereas a trajectory is all about, again, the future prediction of the next location with respect to velocity and acceleration. It also governs path, but we are very much specific towards velocity and acceleration. So whenever you design a path for the robot, you require velocity profile as well as acceleration profile with respect to intermediary points. So this is all about understanding the robots with respect to path planning. So after this, what I need to study, if you ask me, I have studied about forward kinematics, I have studied about inverse kinematics, I have also studied about path planning. So is that it all? Is that completes the understanding about robots? Each and every concept discussed here has a separate syllabus, okay, a separate content which can be studied in a separate, as a separate course, okay. But we are trying to give you an overview about things, so that is why I've confined everything. So after path planning, what we need to study is, we need to study about the torque and force relationship created at the end effector. So for that, you must understand about how the impact is being created when we move the robot with respect to different locations. If we move the robot with respect to a different path, if it is being created, okay. So what is torque, what is force, and why it is very important to be studied? So if you ask me what is force, the force is nothing but the push pull effect created. But should it be studied only at the end effector? If you ask me, it is not like that. We need to know about the torque relationship, torque profiles, force relationship, force profiles created at the end effector as well as at the joints. So it is must for a robot to be learned. So apart from these, we have one more topic called dynamics. So this dynamics is a very vast area where you can diversify yourself when you are ready for taking up the study on robotics. So why? So dynamics is a complete different study. So we think the robot to be as calculated through the specifications, and if we employ that, will it function after creating a path or after putting up the computation for forward motion, forward kinematics problem, after proposing a solution for that? If you think the robot can function, still we have many problems in it. That starts with dynamics. Why? Supposingly, if I handle a weight for a specification of 1 kg, if it is taken to a different location from the starting point, we may have disturbances created by the weight, which may impact the operation of the robot. That is, I may have the robot planned based on the specifications, but in spite of these, if I try to move the robot, the external forces which is present in the environment, because we live in an environment where external forces are present. The forces can be an interference because of the air dynamics. It may be a force created because of the oscillation of the weight. It may be a force created because of the link structure which is provided in the robot. All matters. So dynamics is a very big concept for studying. So for that, they will prefer Lagrangian mechanics for understanding the dynamics. We are not moving further into the details about the Lagrangian, but since this is an overview about the principles behind robotics, I have started from the introduction part where the word is being coined, and we traveled into the history parts, and followed by that, the science behind robots based on the industries. So this is all about the session and the future scope. If you ask me, what can I do when I take this robotics as a study? So you may see about the drone technologies, you may see about different bot mechanisms, you may see about the automated defense mechanisms employed